Hi Year 12, I thought this week that I'd do a video and next week as well, starting to have a look at radioactivity. Next week we're going to look at half-lives and activity in much more detail than GCSE, looking at logarithmic graphs. Today we're going to look at the following: properties of alpha, beta and gamma radiation and how to test for them in a lab. You've done this at GCSE, but it's really important that you know the techniques. So I've got a series of short videos which I've imported in, which were done as training for staff. And so those are the same experiments that I use. So you can look at alpha, beta and gamma properties. You can look at the nature, penetration through materials and range in air, and the techniques used to investigate their properties. Once you've done that, I want you to pause and do some work and then come back to the video at a later stage and look at nuclear decay equations. Again, you've done these at GCSE, but you need to know them more detail, and you need to know both beta minus, beta plus, as well as alpha and gamma radiation. You'll be able to balance nuclear transform equations, and you should be able to, on a graph of protons against neutrons, be able to say or predict what type of decay an unstable nucleus will go through depending on where it is on this graph. And finally, understanding decay chain series. So the first thing I want you to do is have a look at this video. Alpha particles are highly ionizing, so they work really well in cloud chambers. You're going to watch two short videos. One is how to set the cloud chamber up, and the other one is a really good animation so you can really see what's happening in it in terms of ionization. One thing to look out for in the video is when the alpha particles come out of the source, they are emitted at about a tenth the speed of light, but they only travel about a centimetre in air, and you'll notice the tracks are all about the same size because alpha particles are all emitted at about the same energies.
We're now going to have a look at the cloud chamber. The first job is to put the alcohol around the edge.
Why use alcohol?
Alcohol is a dipole molecule, meaning that it'll be attracted towards the ionised air particle. When I find the source for the cloud chamber, you'll see it's mounted in a cork in a metal tin. I'm going to pick the source up by the cork, and I'm not going to touch the end which is covered with the luminous paint which contains radium. I carefully thread it through, and the cork also seals the chamber and stops the alcohol vapour from coming out. So now it's time to put the dry ice into the bottom of the chamber. I'm not going to pack it to the top, I'm just going to put enough in to cover the bottom of the chamber, and then put the sponge in to hold it in place, and attach the bottom and turn it to lock it in place. Once you've done that, you can turn the chamber back over. We can use the small wedges to ensure that it's flat on the table. And we're now ready to illuminate the chamber. You can then view from the top of the chamber to see the tracks produced by the ionising radiation. I've got the tracks from the radioactive source leaving their trails as they streak through the saturated vapour. But on the small scale, let's follow one of those particles as it ionises the air on its way through. In slow motion, let's have a look and watch the alpha particle getting close to one of the air particles, ripping an electron from the outer shells, and you'll see them scattering away either way. So it gets close, it strips the electron, and carries on moving. So as soon as the particle is ionised, the alcohol starts to be drawn towards it, clumping together and starting to form the track that we've seen in the cloud chamber. If we zoom out slightly from that, you'll see this is happening around every single particle that's been ionised, and that will leave a trail of the alcohol.
The next one to look at is the range of alpha particles in air. We use a spark count to do this in a lab because alpha particles are highly ionising. This video shows you that, and then again in animation. Some staff make the mistake of trying to show this with beta and gamma, and of course they won't work with a spark counter because it doesn't produce enough ionisation of the air.
The spark counter can also be used to look at the absorption properties of alpha radiation using an americium source.
I'm going to hold the source so the alphas are being detected. When I put the paper in the way, it stops. To show that paper stops the alpha particles from getting through. I can now point out the range of the alpha particles, which is a few centimetres in air.
A more controlled way of handling the radioactive source is to mount it in a dowel rod and clamp it in a retort stand.
We can see the mesh across the top, which is connected to the negative side of the power supply, and the wire underneath, which is connected to the high voltage positive side. As the ionising radiation comes in, it causes the sparks to happen. As we zoom in, an alpha particle is coming from above, and it ionises one of the air particles between the gap. That's then accelerated upwards, and that causes a cascade of ions hitting each other, which we see as a spark. Each ionisation particle coming in is going to cause a spark of its own.
Next, I want you to look at the properties of beta particles using this video.
For this experiment, use a pure beta source such as strontium-90.
I can get an audible representation of how much radiation I'm measuring. The first thing to do is to show that, unlike the alpha particles which are stopped by paper, the beta particles aren't. So putting a piece of paper in makes no difference at all. However, if I bring a piece of aluminium in, we can hear that the beta particles are completely stopped, because the range of beta particles is a few millimetres of aluminium. The other thing we can demonstrate is the range of the beta particles in air, and if I move the source away from the detector, you'll hear that the count rate decreases. And notice that the range in air is significantly larger than the alpha particles, which was 2 or 3 centimetres. We're at tens of centimetres and still getting a reading on the counter.
This video shows how beta particles can be deflected by a magnetic field. Remember, electrons are charged particles, so when they move, that is a current. So from GCSE, if you remember, F equals Bill, current in a magnetic field experiences a force.
This experiment shows that beta particles are negatively charged.
I've got them at an angle to each other so that the detector is not collecting the radiation as it's fired from the source. The aluminium plate is to block any stray beta particles from going straight into the Geiger-Müller tube. I can then use a magnetic field to deflect those beta particles around the shield into the detector. So as I bring the magnetic field in, the count rate increases significantly as they're deflected into the detector. And just to confirm that it's not the metal plate, if I reverse the field and bring it back in, I can see the count rate doesn't change because they're not being deflected towards the counter. I can confirm this with Fleming's left-hand rule, with my first finger representing the field, my second finger pointing in the opposite direction to the beta particles, and my thumb showing the direction that they will be deflected into the detector.
Finally, this video shows you how to demonstrate the range of gamma in air and the properties of gamma radiation.
This time I'm going to use cobalt-60 as my gamma source. So I'm going to mount the gamma source above the Geiger-Müller tube.
That's quite a lot lower count rate.
There's two answers to that. The first is that the Geiger-Müller tube is not as good at detecting gamma rays. And secondly, the number of gamma rays produced by this source is quite low. If I put the aluminium in the way, the aluminium is not absorbing many of the gamma rays as they pass through. However, if I introduce some lead, it's only with a couple of centimetres of lead in the way that the count rate is significantly reduced, because gamma rays can pass through lead, but several centimetres starts to significantly reduce the number getting through.
Reduced but not stopped.
Yeah, to completely stop the count rate, we have to have several tens of centimetres of lead.
Why is it that lead stops it as opposed to another metal like aluminium?
Okay, the aluminium itself is quite a light metal. Its density isn't very high, as opposed to lead, which is very dense, which will absorb the gamma rays as they pass through.
Handling the absorbers with the bare hands is quite safe. The problem arises if you're tempted to put the absorber close to the source with your fingers. So we always recommend that an absorber should be handled with forceps if you've got a radioactive source nearby.
The other thing that we can start to try and show with this setup is how the range of the gamma rays in air is linked to the inverse square law. So hopefully if I double the distance they are away, the count rate will go down by a factor of 4. So at the moment my source is roughly 4 centimetres away, and if I double that to 8 centimetres, the source will now be counting at about a quarter the count rate.
So we've covered all the first section with those videos that you would have seen in lessons with me demonstrating them. I want you to now stop the video, go back to chapter 25.1 and make your own notes on the properties of alpha, beta and gamma radiation, how to test for them and answer the summary questions. The second part is nuclear decay equations. What I've done is a series of written animations which I've talked over, which produce a spider diagram of everything you need to know for this section. In order to work out which way unstable nuclei decay to become stable, we need to plot a graph of protons against neutrons and look at the stable region. So nuclei that are on this line or very close to this line are stable and therefore don't decay. You'll notice that for the first proton number up to 20, proton number and neutron number are the same, but as the nucleus contains more protons, it needs excess number of neutrons in order to become stable. Nuclei on the right side of the curve are proton rich and therefore have too many protons, so they lose protons to become more stable. Nuclei on the left hand side of the curve are neutron rich and so lose neutrons to become more stable. Unstable nuclei that decay by alpha radiation are in this part of the graph, which means that they are heavy with a proton number usually above 80, and they are proton rich, having too many protons. Alpha particles are helium nuclei, which consists of 2 protons and 2 neutrons, no electrons, and so they've got a 2+ charge. We can write a general equation for the decay by alpha, where A is the nucleon number of protons and neutrons, Z is the proton number, and X stands for the parent nucleus. So writing the helium nucleus first, the alpha particle, and then Y stands for the daughter nucleus, and so the top number we've got A minus 4, and the bottom number is Z minus 2. This is so conservation of nucleon number and proton number are conserved. An alpha particle is emitted from the nucleus at about 0.1 the speed of light. They roughly have all the same energies. To see what's happening on the neutron-proton graph with alpha decay, we can sketch a small graph showing the changes. Starting with N on the y-axis and the original Z on the x-axis, we've got the parent nucleus. The daughter nucleus has 2 less protons and also 2 less neutrons, and so you can see the transition towards the stable region. This can also be shown on the main graph with the alpha particles moving towards the stable region. A quick example of alpha decay is radium into radon. You'll always be given what it decays into. The key thing again is to draw down your alpha particle first, and then you can fit the numbers in. So now we're going to look at beta minus decay. This happens in neutron-rich nuclei, which are unstable, and they move towards the right to become more stable. So beta minus decay are neutron-rich nuclei. They are electrons that are emitted between 0.1 the speed of light and 0.9 the speed of light, so they have a whole range of energies. Because they're neutron rich, a neutron changes into a proton and also an electron, and this is emitted at near the speed of light, and this is your beta particle, but it also produces an anti-lepton neutrino. It has to produce an anti-lepton neutrino because electrons are leptons, and for lepton conservation you've got no leptons on the other side of the equation, it's just a neutron, therefore you have to have an anti-lepton neutrino to cancel out the number. This is not part of the A-level syllabus, but that's why it's produced. So a reminder from the work you've already done, it's the weak nuclear force that's responsible for this decay from the neutron to the proton, and of course it happens because one of the down quarks changes into an up quark. In a moment you'll see why the electron has the symbol 0, -1. So again we have the parent nucleus decaying, and because the number of protons and neutrons stays the same in all, A doesn't change. Sorry, the daughter nucleus should have the symbol Y, and of course the parent nucleus has lost one neutron and gained a proton, so the daughter nucleus has one more proton than before, so it's Z+1. So now you can see why the electron has to have the symbol 0, -1, so the nucleon number and the proton number match for conservation. Again, we can show how the movement of the parent to daughter nucleus occurs on the graph by drawing a sketch of N, number of neutrons, against Z, number of protons. So the daughter nucleus has one more proton, so that's Z+1, and one less neutron, so that's N-1. So you can see how it changes. Finally, a quick example. Helium changes into lithium by beta- decay. You can see by drawing the beta- sign first, it allows you to balance it easily. Lighter nuclei in the proton-rich region decay by beta+, which is positron emission. So beta+ decay is proton-rich. A positron is emitted between 0.1 and 0.9 the speed of light. Because the unstable nucleus is proton-rich, a proton changes into a neutron plus a positron, a positive electron, and a neutrino. The neutrino balances out the lepton conservation. To explain that in terms of quarks, we have a proton, which is an up-up-down combination, and one of the up quarks changes to a down quark to produce a neutron. So the general equation for beta+ decay, we start with a parent nucleus, and this time one of the protons is changed into a neutron, so the proton number goes down, Z-1. The nucleon number of protons and neutrons overall stays the same. Again, the weak nuclear force is responsible for beta+ decay. Finally, plotting the neutron-proton graph gives us the following. We have one more neutron and one less proton. An example of beta+ decay is fluorine into oxygen. And just like beta+ decay, it's the weak nuclear force that's responsible for beta- decay. So what about gamma decay? We know that gamma radiation is a photon of very high frequency in the gamma region of the electromagnetic spectrum. Therefore, it travels at the speed of light. After alpha or beta decay, the daughter nucleus is often excited, has surplus energy, and so loses its energy by emitting gamma radiation. We won't see this transformation on a neutron-proton graph because the nucleus still stays the same element, it just loses energy, and so this is the general equation for gamma decay. Finally, a big misconception is once a parent nucleus has decayed into a daughter nucleus, it is stable. This is not usually the case. It's normally still radioactive and decays by a different type of radiation, or the same, but will have completely different half-lives to the previous parent nucleus. finally, on this section, a misconception is that once a parent nucleus decays to a daughter nucleus, that it's now no longer radioactive. This is not usually the case. So this is an example of a chain or a decay chain to something that is stable. So you can see that radon 226 has a half-life of 1,620 years, and when it decays by alpha, but also emits gamma because it stays in an excited state, and it decays to radon 222 isotope. This only has a half-life of 3.82 days. Again, it decays by alpha, so you can see how it's moving on the proton to neutron graph, to polonium, which only has a half-life of 183 seconds. It decays by alpha again, and then you can see it decays by a series of beta and gamma, then alpha, then beta, and then alpha, finally to lead-236, which is a stable nucleus on the main graph, and therefore it doesn't decay any further. Go on to chapter 25.2, make your own notes on alpha, beta plus, beta minus, and gamma decay, and then do the questions at the end. I hope this video has helped and it's been a bit more personal than just reading through the textbook, especially in lockdown, and I look forward to seeing you next week. Don't forget to upload what you've done onto Show My Homework so I can just check that you've done it, and do check your answers to the summary questions. Thanks and bye for now.